Imagine a world where engineers can simply describe an industrial problem in plain English, reduce energy consumption during peak grid hours while maintaining production output, and instantly receive a fully executable optimization model, ready to run in Gurobi, CPLEX, or LINGO. This isn't science fiction. It's the future of industrial AI, powered by large language models grounded in deep domain knowledge. But here's the catch. Most current approaches fail at the most critical step, ensuring the generated code is actually executable. Why? Because natural language instructions often lack the precise structure needed for mathematical optimization. LLMs, even when augmented with retrieval, frequently hallucinate missing declarations, misdeclare variable types, or reference undefined symbols. The result? Code that compiles but doesn't solve. A model that looks right but fails in practice. Today, we dive into a groundbreaking method that solves this exact problem. Type-aware retrieval-augmented generation with dependency closure. A system that doesn't just retrieve information. It reasons about dependencies to guarantee executability. Let's break down how this works step by step. Hash the core problem. Structural hallucinations in industrial AI. Industrial optimization modeling. Think battery production scheduling, flexible job shop planning, or energy demand response. Requires precise mathematical formulations. Every variable must be declared, every constraint must reference defined symbols, and every index must be properly scoped. But when you ask a large language model to translate a natural language request into code, it often assumes context it doesn't have. It might use a variable like machine power without defining it. Or it might treat a parameter as a continuous variable when it should be binary. These aren't syntax errors, they're structural hallucinations. And conventional RAG systems don't fix this. They retrieve relevant text chunks, documentation, papers, code snippets, but they treat them as isolated fragments. No graph, no connections, no understanding of what depends on what. So the model generates code using symbols that aren't declared, or references that aren't resolved. The result? A non-compilable, unsolvable model. Hash the solution. A typed knowledge graph with dependency closure. Our method flips the script. Instead of treating knowledge as unstructured text, we build a domain-specific typed knowledge graph, a structured map of the entire optimization landscape. We start by parsing two types of sources. Academic papers to capture conceptual intent. What does buffer blocking mean? What's the role of incentive pricing? Executable solver code to extract actual syntax. How is a variable declared in LINGO? What's the correct way to write a constraint? Each entity, variable, parameter, constraint, objective, index set is assigned a type. Binary, integer, continuous. Time-indexed, machine-specific, product-dependent. This type system enforces consistency. Then we link them via mathematical dependencies. A variable uses a parameter. A constraint depends on an index set. A paper concept aligns to a concrete code construct. This creates a directed graph, a computational scaffold where every symbol has a clear lineage. Hash how it works, from query to executable code. Let's walk through a real-world example. Demand response in lithium-ion battery production. The system receives the instruction. Add a load reduction constraint for the demand response event between hours 16 and 17. Step 1, query understanding. The system parses the intent, adding a constraint and extracts entities. Time window 1617, event type demand response, and target system battery production line. Step 2, hybrid retrieval. Semantic retrieval. Embed the query and match it to relevant paper excerpts, explanations of incentive mechanisms, energy cost structures. Structured retrieval. Start from the target constraint node and traverse the knowledge graph along used-in and depends-on edges. This pulls in all upstream dependencies. Machine power ratings, parameters. Time step indices, index sets. Baseline load values, BREF. Incentive rate, lambda. Step 3, minimal dependency closure. Now comes the key innovation, computing the minimal dependency closed context. We perform a breadth-first traversal from the target constraint, following only critical edges. The result? The smallest possible set of symbols that makes the target constraint well-defined. No extra noise. No irrelevant concepts. Just exactly what's needed. This closure is minimal. It excludes anything not required, and closed. It includes every upstream symbol that could be referenced. Step 4, context packaging and code generation. The final prompt to the LLM includes all typed entities with full definitions and solver-level names. A textual summary of the dependency subgraph. The top semantic snippets for contextual grounding. The LLM's job. Not to reason, just to translate. And because the context is complete and consistent, the output is syntactically valid, semantically grounded, and solver executable. Hash real-world results, 2 industrial case studies. Case 1, battery production demand response. We modified the objective function to include incentive-based load reduction during peak hours. The generated code dynamically calculates energy consumption per time slot. Adds an incentive reward term based on load reduction. Enforces a minimum reduction of 10 kW during the event window. The model solved in under 120 seconds, achieving peak shaving, a 15% drop in energy consumption during the event window, while increasing profit by 0.13% due to incentive earnings. Visualizations show red cells in the machine schedule. Machines deliberately turned off during the event, proving the model didn't just follow rules, it optimized them. Case 2, Flexible Job Shop Scheduling, FJSP. This is a completely different domain. No energy costs, no incentives, just scheduling jobs across machines with precedence and capacity constraints. Our method generated models that reached known optimal solutions on benchmark instances, handled machine unavailability windows without errors, adapted to alternative terminology, e.g., operation start time versus processing start, via semantic links. In contrast, conventional RAG baselines failed entirely, missing variables, undefined indices, syntax errors. Why this matters, the science behind the reliability. This isn't just about better code. It's about reliability, the guarantee that every generated model is compilable, solvable, and free of structural hallucinations. Our ablation studies prove it. Using only academic papers. Syntax errors. Using only solver code. Incomplete logic. Using both. Correct LINGO syntax, proper indexing, and full dependency closure. And the dependency closure mechanism. It's not optional. Remove it and the model fails. Enforce it and success rates jump from 0% to 100%. The bigger picture, a new paradigm for engineering AI. This method isn't just a technical fix, it's a paradigm shift. It moves from semantic similarity to dependency-aware completeness. From retrieving text to reasoning about structure. From hopeful generation to guaranteed executability. It enables non-experts to generate correct optimization models. It reduces debugging time from days to seconds. It unlocks the full potential of LLMs in complex engineering domains. And it's reproducible. The full knowledge base, schema, and code are publicly available, so you can build on it, test it, extend it. Final thoughts. We're standing at the edge of a new era in industrial AI. The dream of translating natural language into executable code is no longer distant. But the path is narrow, filled with traps of missing declarations, type mismatches, and structural hallucinations. This method, type-aware RAG with dependency closure, doesn't just avoid those traps. It maps the entire terrain. It's not just about better models. It's about trust, in the code, in the system, in the future of intelligent manufacturing. So the next time you think about automating industrial optimization, remember, the key isn't just what the model knows, but what it must know to be correct. And now we have a way to ensure it. If you're working on industrial AI, optimization, or LLM-powered modeling, this is the foundation you've been waiting for.